Namaskar. So let's have a look at that what all we have studied in this chapter in inverse trigonometric functions. So we have seen we have started with our review of the trigonometric function, the important property, and then we build up the concept of inverse trigonometric functions, and then we saw some properties for inverse trigonometric functions. So let's summarize that in brief, and then we'll solve some examples with that, and then we'll end this chapter. So let's begin. So for principal value branches of inverse trigonometric functions, right? So the domain and range can be seen as domain and range. So let me make it here in a chart. So let's say this define the function, and let it be the domain, and let it be here the range, right? So now let's see one by one. So let's say if the function is y is equal to sine inverse x, then what is domain? It is from -1 to 1, and the range would be minus pi by 2 to pi by 2. So this range you have to remember, because that whenever you need to find the principal value for a given function, then you should know that in which one is the principal value range. Then you take y is equal to cos inverse x, and the domain would be -1 to 1, and for this range will be again here 0 to pi. If you take y is equal to cosec inverse x, then the range is any real number except -1 and 1, in between the numbers which is between -1 to 1, and then your range would be minus pi by 2 to pi by 2 except the 0, because at 0 it is not defined. Similarly, if you take y is equal to sec inverse x, then it can have a domain all the real numbers except numbers between -1 to 1, and the range can be 0 to pi except pi by 2, because at pi by 2, of course, your this value 1 upon cos pi by 2 is not defined, because 1 by 0 is not defined. And then you have y is equal to tan inverse x. It can have a domain all real numbers, and the range can be minus pi by 2 to pi by 2. Similarly, for cot inverse x, is equal to any real number to 0 to pi. So this is the function domain and range for the inverse trigonometric function that we already seen, and it is important to know, because when we are going to calculate the principal values for different inverse trigonometric functions, then these value will be very helpful, because they are only, this is the domain and range where they are 1 1 and 2, and then you can have an inverse defined, otherwise it is not correct. So this is about the function domain and range. Now let's have some further review of the property which we have studied in this. So let's have a look on the one property we just saw, is that if we write sine inverse x, so it is not equal to sine x of inverse, right? So that you should not confuse, because this would be equal to 1 upon sine x, which is equal to cosec x, right? So it is not the same thing. So this is the function is not equal to the inverse of sine x. That is one important point. The other important point is that so the value of inverse trigonometric function which lies in its principal value branch would call principal value, right? So any trigonometric function, let's say y is equal to f inverse x. So if the principal value branch between let's say x1 to x2, this is the principal value branch, the values would be called principal value. So for example, we just saw that between minus pi by 2 or 0 to pi or whatever. Now let's have a look at the properties of the for assuming that they are having the suitable domain values. So let's have a look one by one. So for example, we saw that y is equal to sine inverse x. This implies that sine y is equal to x. Similarly, we can write s is equal to sine inverse y, s is equal to sine y, and it would imply that y is equal to sine inverse x. Okay, and of course choose your domains appropriately so that they are defined, and because the inverse exists for that. The other property which we have seen is that if sine of sine inverse x is equal to x, and similarly you can write sine inverse of sine x is equal to x. The other property we had seen about inverses, so that was sine inverse of 1 by x, that we wrote it as cosec inverse x. Cos of 1 by x we wrote as sec inverse x. We wrote tan inverse 1 by x, this is inverse 1 by x, we wrote as cot inverse x. Similarly, we saw for some other functions. So for example, let me extend here again like this. So we the minus type, so we wrote, so for example, cos inverse minus x, it can be written as pi minus cos inverse x. We can write cot inverse minus x, and that can be equal to minus pi minus cot inverse x. We can have a sec inverse minus x is equal to pi minus sec inverse x. So that is one type. The other type for the minus x type, like minus sine inverse minus x, you can write it as minus sine x. You can have cosec inverse minus x is equal to minus cosec inverse x. You can write tan inverse minus x is equal to minus tan inverse x. Okay, so this is another type of the properties. Now for the sums, so let's say if we have sine inverse x plus cos inverse x is equal to pi by 2, we have tan inverse x plus cot inverse x is equal to pi by 2. We can write cosec inverse x plus sec inverse x is equal to pi by 2. The other type we saw for tan, so tan inverse x plus tan inverse y, it can be written as tan inverse x minus y upon 1 plus xy, right? Sorry, here it is plus here, right? So x plus y 1 upon minus xy, right? Similarly, you can write tan inverse x minus tan inverse y. It can be written as here it will become x minus y, and at the bottom x 1 plus xy, right? Other for tan sum, it can be written as tan inverse x plus tan inverse y, and that can be written as pi plus tan inverse x plus y upon 1 minus xy, where of course your xy should be greater than 0, and individually xy should be greater than 0. Okay, so the other functions we may have here is the for 2x type. So for example, 2 tan inverse x can be written as sine inverse for appropriate domain values, remember, so that validity you have to see squared, and then it can also be for another domain value range. It can be written as 1 upon x square upon 1 plus x squared, or it can be written as tan inverse 2x upon 1 plus 1 minus x square. Okay, So these are the function properties for inverse trigonometric function, which is very helpful and all derived from your trigonometric function, right? So if you remember the trigonometric function, you can easily derive, but if you remember directly it, then it is easier to solve your problems. Mostly in a competitive exams or in a board exams, if you are getting your objective type questions, and it makes lots of good objective questions, right? You will be testing your understanding and knowledge in that. So there it is very helpful. So just keep remembering it, and it's very easy. You see the symmetry and you'll be realizing that it can be easily remembered. So this is about that property. Let's solve some examples and then we'll end this chapter. So let's see what examples we can have in this. So the first example, I have selected one. So let me have the first example where I need to find the value of sine inverse sine of 3 pi by 5. Okay. So how to find it? So as we assume, you take we take sine inverse sine x is equal to x, that we know. So similarly we can write sine inverse of sine 3 pi by 5 would be 3 pi by 5. But what is the inverse function, right? Sine inverse function, the principal value branch is what for this? Minus pi by 2 to pi by 2, we just saw before. So and if you see, this 3 pi by 2 is not element of this principal value branch, right? It is not element of this minus pi by 2 to pi by 2. Then what to do? Then you have to solve this further, so that you can get a value which lies in this, in between this range, right? So we can write the same sine 3 pi by 5, you can write it as sine pi minus 3 pi by 5. It can be equal to sine 2 pi by 5. Okay, so it means that you can write sine inverse sine 3 pi by 5 equal to sine inverse sine 2 pi by 5, which will be equal to 2 pi by 5. And now you see that 2 by 5 is element of your minus pi by 2 to pi by 2, right? So it means the value of sine inverse sine 3 pi by 5 would be your 2 pi by 5. This is your answer, right? So this is how utilizes that understanding of the principal value branch and where it should lie, because there it is inverse exists, and then you can find the appropriate principal value for such. So this is one type of example. The other one we can have a little longer though, but it will have a little understanding of how to use the techniques to solve such problems. So let's say we need to find the value of this sine inverse 12 by 13 plus cos inverse 4 by 5 plus tan inverse 63 by 16. So we need to solve this. So let's solve. So assume that x is equal to sine inverse 12 by 13, y is equal to cos inverse 4 by 5, and your z is equal to tan inverse 63 by 16, right? 16. So you can write this as this is your inverse. You can write it as sine x is equal to 12 by 13. Here you can write cos y is equal to 4 by 5. Here you can write tan z is equal to 63 by 16. Okay. Now you can find the cos x and sine y, how you can get it. So let's see, you have cos x. So I want to find, so how can I write? Cos square x plus sine square x is equal to 1, you know. So utilize that property, and here you can write cos x is equal to 1 minus sine square x, and you just put that above value. So you can have 1 minus 12 by 13 whole square here. So you will get 169 minus 144 divided by 169 is equal to under root 25 by 169. That would come 5 by 13. Similarly, you can have your sine y. So that would become 1 minus cos square y. Okay, you have cos y here. So you can have 1 minus 16 by 25. You calculate, you will get 9 by 25. It will become 3 by 5. Okay. So now since you got sin y, cos x, sin x, so you can find tan x. So what would be tan x? Is equal to sin x upon cos x. So you put the values of sin x is 12 by 13 and cos x you just calculated is 5 by 13 divided by 5 by 13. So you get 12 by 5. Similarly, you find value of tan y. You have sin y upon cos y. You write it and then you put the value of sin y, which is 3 by 5 here, and divided by 4 by 5. Okay, so you solve, you will get 3 by 4. So you have tan x, tan y. Now let's solve further. So now again, now utilize that trigonometric function property here, tan x plus y, and that we can write is tan x plus tan y upon 1 minus tan x tan y. Okay, now put the values of tan x, tan y we just calculated here. So 12 by 5 plus 3 by 4 divided by 1 minus 12 by 5 into 3 by 4, and if you solve you will get 20 here, 48 plus 15, and here at the bottom it will be 20, this 20, and here 36. So if you solve you will get 4 3 3 3 9, now 5 and 4, so you will get here somewhere minus 4 by 5. Now you solved it, so you will have 63 divided by, it will go up 4, so it is minus 16, right? So it will be minus 63 by 16. Okay, so now you can take easily the inverse for that. So you can write x plus y is equal to no, here we just saw here, right? It is given the just we assumption that 16 over 60 is equal to tangent. So you just replace that value with the tangent. So what we get? So we get x plus tan x plus y is equal to minus tan z. You can write it tan pi minus z, that will give you minus tangent. Again it is from the trigonometric function property in the very first lecture of this chapter we discussed. And then you take the inverse of the both sides, so you will have x plus y is equal to pi minus z, implies x plus y plus z is equal to pi, right? So this is what we wanted to calculate the value. So it means you put the x values, so here sin inverse 12 by 13 plus cos inverse 4 by 5 plus tan inverse 63 by 16 is equal to pi, right? So the value we found, just found that if you solve you will have answer pi. So very nice example. So this is now we complete here the summary of the chapter and how we utilize even in the inverse trigonometric functions. It is very important to remember the trigonometric function and their properties, so even solve and understand these problems. So this is all for this chapter, and we end this chapter here, and then we'll meet you again where we'll start in next chapter about matrices. So see you there. Thank you.